Hello, good morning. Welcome to Micromaterials UK European User Meeting. Very glad to see that we have quite a nice number of people joining, which is fantastic. This is traditionally something that we had as a face-to-face meeting in December every year. Given the current state of restrictions, we've moved this online now. I hope we'll be and condensed it. Of course, previously it was a whole day's meeting. The last one we did in Southampton in 2 years ago, and previous ones now I think it was Warwick from my memory. So we've condensed it into the morning. Be some short, sharp talks. Hopefully very interesting. There was a focus through the meeting on somewhat on nanotribology and testing of materials, as well as general nanomechanical measurements. And I hope people will find it interesting. I've got a couple of slides just to put up, just to explain who Micromaterials are. Hopefully, a lot of you will know already. We basically make nanomechanical measurement devices. You can see the three main products that we manufacture. The Alpha, which is very much the base unit, single head instrument. In the middle is our Vantage instrument, which is capable of carrying two heads and working to higher temperatures. The instrument on the right is the Extreme. That's our system that works inside a vacuum. So it's a full system that's inside the vacuum, allowing us to go to higher temperatures and to study materials with no high temperatures, with no oxidization of materials, or of course indenters. That's now installed in many countries around the world, across Europe, across into Asia. So they're the three tools we tend to base our work around. But of course, we are a modular system, so I'm not going to go into this slide, but other than to say that our philosophy at Micromaterials is to provide high-level research instruments, high-level application support. We are basically producing. Very rarely do we produce two instruments absolutely the same, but you can see on the base system, this is the Vantage system. You can choose loading heads, you can choose your experimental modes, imaging modes, environmental modes, study modes, temperatures up, in this case of the Vantage, up to 850 degrees centigrade, and other experimental add-ons. Our systems are generally retrofittable, so we can retrofit these devices to current systems in the field. Depends on the age of the system how easy that is. Generally, upgrades are done in the field as a general rule, and therefore relatively cost effective. There's no shipping back of instruments. That's the philosophy we have. The philosophy, therefore, is to keep your instrument completely updated and completely in line with current specifications. We also do a series of these technical seminars. There's probably a dozen a year at least, as well as contributing to other meetings and to other ventures, other programs from a philanthropic type point of view. Our interest here is in research, R&D. As the main owner of the company, I have a PhD, and this is really what we're all about. All about research, pushing the boundaries, and ensuring that our customers can do leading edge research. I'll do a quick advert at this point. My last slide for the next meeting we have is on 27th of January. It is an Indian-focused user meeting. with current users in India, and in fact also from the US, and from Indian expats from the US and UK who will be speaking. So let me just flag that up as the next meeting, as you should always mention the meeting coming up next. That's the end of my slides. I want the format of the meeting coming up. Hopefully you've seen the agenda, and talks will be approximately 20 minutes long. There will be a time at the end then for some Q&As directly. If you have questions, please write them in the chat box. The chat box, Sam is excellent at picking up questions in the chat box, and he will order them. We normally take questions simply in the order that we get them. We do try and answer every question that comes in. If we don't have time, we will then try and make time at the end, in the Q&A forum at the end. But also, the speaker may respond directly to you during the course of the meeting on the chat box. So if you have questions, please put them in the chat box. That is the only way that we will get questions to our speakers. And as I say, Sam will pick them up, and he does a great job of lining them up, so we answer them as quickly as possible at the end of the meeting. You will see during the course of the next 2 hours that there'll be some polls that come out. These are basically polls of interest. To see the type of audience that we have, and you'll also have the opportunity to download some handouts as we go through, which will give further information on what we're talking about. They will appear in the right hand corner, and you'll also see in the left hand corner some links through to web pages that will come up again during the course of the meeting, and LinkedIn pages, and how to get further information on both the speakers and market materials. And actually Sam just pointing out that he has some Christmas themed fun questions as well, which gives me cause for concern, but I'm sure they'll be fine. I hope it's enjoyable. I hope it's an interesting 2.5 hours. With that, I'll hand over to our first speaker, who's Professor Robert Wood from the University of Southampton. He's been at Southampton, I think, since about 1993, when he came from BP Research, BP Research Labs, which memory says was probably down in Surrey somewhere, but I could be wrong. It's a long time ago. He is founder of the UK National Centre of Tribology, NCATS, the Dean of Research at Southampton. He's got a lot of specialised topics: rain, cavitation, solid particles, erosion, and he's looked at a number of interesting subjects. I noticed the one that struck me was helicopter blades, but there's a lot more. I remember seeing his lab a couple of years ago with the toothbrushes all working, and that was a nice study. I think of him every time I brush my teeth now. Robert, I'll hand over to you to take the stage.
Thank you, Chris, and good morning or afternoon or evening, everyone. So I'm just going to talk a little bit about cold erosion of some polyurethane systems, coatings that are being considered for wind turbine blade or leading edge protection. So this work came out of a Framework 5 European project, Wind Trust, and primarily it's just been advanced by some students and a postdoc that was at NCATS, is now a lecturer at Portsmouth, Jugita, who I think may be listening as well. So good morning, Jugita. And it has been written up in WARE for those that are interested. So why are we interested in cold erosion? I mean, clearly damage to the leading edge can lead to quite dramatic drops in the efficiency of energy extraction from wind. So you can get up to about 25%. The technology that people are turning to are these thermoplastic polyurethane coatings, and there's a variety that you can choose from. And we've found that there was little that we could find in the public domain anyway that looked at the effects of temperature, particularly low temperatures. So that's really what we wanted to do in this study. So we were trying to compare sort of ambient room temperature type studies with lower temperature to see just what the resulting erosion and micromechanical properties might be of these systems. So just to reassure you the need for this, obviously, this is a map of temperature, so you can get down to minus 30 in parts of Europe, and obviously when it's cold, the energy demand goes up. So wind turbines, wherever they're situated, need to extract energy. We've sort of focused. I mean, the main damage obviously is caused by liquid droplet impingement. Difficult to do that at low temperature experimentally, so we did switch to a solid particle erosion facility, and that looks pretty unexplored at the time, but it is relevant because there are particles, hail in particular, that might hit the blade. So it's not completely, but they are quite different. The erosion performance against liquid droplet will be slightly different to solid particle. So the methodology was to do some experiments at low temperature. So this is our air sand erosion facility up at the Science Park at Southampton, and it just allows us to accelerate particles up to about 280 meters per second, and impinge at different angles. You can look at different particle sizes, particle concentrations. This was modified by a group design project, our fourth year students, to allow us to cool the system. So there is obviously a liquid nitrogen supply in, so that the sand comes into this sort of red bit here, into accelerated airflow, it's into a venturi, then it's slightly expanded, mixed with the liquid oxygen, and impinges on the sort of grey sample there, and there is temperature measurement just below the sample to allow us to control the sample temperature. So that's the erosion experimental side of things. The erodent that we chose was sort of semi-rounded quartz sand, had quite a wide particles, although the average is just under 100 microns. The distribution here is quite broad, so there were quite a number of small particles I'll come on to later, and equally some larger than 100 in the mix there. So that was the type. So they are quite angular, and there are some sort of rounded, so you're likely to get a slight mixture of erosion mechanisms just because of the shape of the sand. The systems that we looked at here, there was so the 3M is the sort of standard tape, so we used that as a sort of bench line, if you like. So that was one layer thick of the polyurethane 3M tape on the glass fiber substrate, which is a typical makeup of a blade. And then we were looking at a commercially brushed system that was slightly more complicated. It had 3 brushed layers of polyurethane, and it had an interlayer of polyester, and then the fiberglass substrate. So quite a complicated system. So that's what we were looking at. And as you say, we tried to operate the tests, the erosion tests, at ambient, so at 25 degrees, and then with the cooling system that the students deployed, we could go down to minus 30. So this is a fairly sort of basic test. So you weigh the sample before. It's quite difficult with polymers. So we weigh, and as accurate as we can to try and get some assessment of volume loss per rodent impacting. The sand concentration, as you can see there, 1.3 10 to the minus 4%. The velocity was calibrated using a high-speed video camera, but with the size distribution that I mentioned of the sand, it was somewhere between sort of 60 and 75 meters per second. And we did the tests at two angles, primarily, for polymers, you'd expect the lower angle to give you slightly higher erosion than you get at 90 degrees. The other way around, if the surface is brittle, you get more erosion at 90 than you do at 45. And then obviously we use the micromaterial system to do some, get some measurements from the system using their nano indentation Vantage system, both at ambient at minus 10. So that was the so the nano indentation. So there was this cooling stage that we use that you can cool both the indenter and the sample, and so we were interested in going down to, well, from ambient down to minus 10, and you could then do some controlled sort of depth sensing work to look at the mechanical properties, the hardness, Young's modulus, etc., from the systems. And we were hoping that would then give us some insight into explaining the performance that you get from the erosion rig. That was the plan, anyway. So just quickly some results. So the bottom line here is that you can see that we've got in red, or if you can see the red on the left-hand bar charts here, are for ambient, and the sort of blue are the colder ones. So there is an influence of angle, and there's certainly a very big influence of temperature. So as you go down to minus 30, the erosion rate dramatically increases, and then obviously there's a subtlety between normal impact and 45. So those were the basic results, and we plotted them here. As I say, we measure the mass loss, convert that to a volume loss, and then we know how many particles impinge. This is quite a large sample area, so most particles will impinge onto the surface, so you can get a volume loss per impact of sand, and that's in cubic microns, a very small volume loss per impact. So then you can look at this ratio, as I say, the difference between the erosion rate at 45 degrees and at 90 tells you whether you've got a ductile system or not. So if this ratio is above 1, then it's ductile. If it's below 1 or around about sort of 0.5, it's brittle. And obviously we were anticipating actually some increase in brittle behavior as you go down in temperature, but we didn't actually see that. As you can see, the numbers are quite high for both systems. They go higher, so they're way above 1. So there is an increase in ductility from the crude mass loss rates against ambient. So that was interesting. And if you then looked at the samples that we so the other, well, these are the samples that we pictured after the test. So the top row there, or at 90 and at 45 on the bottom row, ambient cold for the polyurethane brushed system against the 3M tape. There is a sort of discolor, they're all sort of blackened, discolored in some, and we haven't quite bottomed that out, but that is possibly a clue. Yeah, so you can see the scars and depth varies depending on temperature. If we look at, so this is at the brushed polyurethane, the 3 layered on top of polyester system. There were some quite dramatic pit features here, and also you could see some either fragments or embedment of the small particles in the system, in the actual coating, but you've got quite concentrated loss of your coating, which is obviously undesirable here. But you do get some embedment, which will affect the mass loss. You sort of get a mass gain because you've caught sand in the system. We looked at sectioning and to see just what was happening subsurface. So again, this is the 3 layered brushed polyurethane system on top of a polyester, and then you've got the fiberglass on the right. So from the top surface is on the left here, and then you end up into the fiberglass to the right, and so you've got the uneroded system on the left hand side. In the middle you've got the ambient case that's been eroded for an hour, and on the right hand side you've got cold erosion after about 15 minutes. So the things to note, obviously you can compare the uneroded to the ambient. The one thing that is quite evident is the cracking, or it looks like you've got some delamination between the polyethylene and possibly the polyethylene and the polypropylene layers, and some failure within the polyethylene itself, even at ambient temperatures. So that is a concern. So whatever erosion's doing, it's starting to disbond the 3 layers of polyurethane. If you get colder, you also get cracks in the polyurethane system. Slightly, you could sort of argue it's sort of 45 degrees, a slightly different type of crack system, but that's only after 15 minutes. So it would appear that the polyethylene, and it's nowhere near its glass transition or anything, so it would appear to be subject to cracking, which is undesirable because, you say, undermines the polyurethane, and you can see there's a huge amount of erosion on the top surface of the polyurethane. So if you then look at the surface profilometry, if you sort of, a U shape suggests slightly more brittle perhaps behavior depending on the angle of particle attack, because you get a spread of angles. But if you go to the cold one, you get a much more complicated profile, some pitting and a sort of more W shape, showing us that we have a little bit more ductility and ductile process going on as you go colder, which was slightly unexpected. And you can see there's some optical microcross here of what the surface looks like. So the mechanism of erosion is changing as you go down in temperature. This is probably the most interest to micromaterials users. So what we have done here, we've done some hardness measurements and extracted the Young's modulus and just reporting it here as H/E ratio and plasticity, primarily because and this is plotted against temperature. So what we were looking at is just what happens against lowering the temperature. And if you look at the right hand side, the plasticity index, you see that the polyurethane starts quite high and then drops as you decrease the temperature, which means that it's bizarrely it's telling us it's getting more elastic, more elastic. Where if you look at the top surfaces, both the 3M and the brushed polyurethane, the values go up. So it's telling us that this is getting closer to some plasticity, and it's the same sort of inverted relationship between the H over E, which tells you the amount of elastic strain a surface can take before failure. And as you go down in temperature, the polyethylene sort of goes up a bit, and that's a bad thing really. If you then look at the top surfaces, they decrease with temperature. We have plotted on the glass transition temperature because we were told that it was typically -5 to 5 degrees, but actually, if you look at the literature for polyurethane, it can be right down to between -15 and -50. So we're not sure that that glass transition is actually true, because we don't seem to be seeing a clear transition to brittle behavior here. So so it's an interesting set of results where the polyurethane is behaving quite differently to the polyethylene, which it's on top of. So really just to draw this to some sort of close, I mean, it's opened up a few questions really as to, we didn't fully know, I don't think anybody does, how to correlate polymer erosion with any properties. So obviously we've just measured hardness and Young's modulus here. Whether that is actually, or they are the properties that are controlling erosion and the erosion mechanism is arguable. But what we can say is that the plasticity increases with the reduction in temperature. So it's telling us that the system is allowing more plastics and more flowing of chains over each other at low temperature. And similarly, the H over E ratio reduces with reduced temperature, so it's less resistant to plastic deformation at low temperatures, and it's consistent really with a more ductile system or mechanism of erosion at low temperatures, which is probably we'd like to probably take it slightly lower in temperature just to confirm we do actually get into a brittle regime, which is what you probably would expect. But it's sort of good news if you're going down to -30, then it doesn't appear you get brittle behavior of your coating. So just some conclusions then. So the erosion rates definitely are higher with lower temperatures for the polyurethane. There's cracking at the PE layer, which would need to be sorted out going forward, because that will take the service life of the top coats down. It looks like it's more ductile at low temperatures, which is a surprise. You've got nanoindentation confirming that plasticity index increased at lower temperatures. The blackening, and if you look at the literature, there is some work suggesting that very locally there are thermal inputs possible here, which may well explain some of the processes. So it may be that local heating means that the polymer behaves quite differently to what we perhaps were expecting, and sort of plastic mechanisms occurs giving enhanced loss, and it might correlate to the blackening of the samples as well. I mean, there are other possibilities of stress wave reinforcement or shear stresses that might be explaining why you've got the cracking of the polyethylene underlayer there. So I think we've created more questions than we've perhaps answered, but I think we did answer one thing. We don't, in these temperatures anyway, get this system to behave in a brittle way, and actually but it is eroding at a higher rate. So that's really what I wanted to say, and thank you very much for listening, and very happy to take any questions now.
Robert, the questions we have coming in, just looking at the top, I've got Ben. First one I saw coming was Ben. Did you see any differences in indentation creep behavior at lower temperatures?
I'm not sure we looked at that, Ben, but Jagita, who actually made the measurements, might actually be able to say whether we did or not. Because I think I can't remember what the dwell time was. I think it was probably 10 milliseconds or something like that. So I'm not sure that we looked at that specifically, but you're right, we could go. I mean, something unusual is happening in the polymer, even with the nano indentation, sort of low strain. So we should look at that.
Okay. Then the next question was from Jan. Said that yes, you're right. It's difficult to correlate mechanical properties to rate of erosion. Are you planning to use some scratch test or pin on disc test in the future?
Yes. Well, we did actually do some scratch tests, but I'm not sure we were able to completely complete the series that we had of the materials that we had. So yes, we have looked at that, and we do need to do more of that, because that would also be a very useful thing. Yeah, hadn't thought of pin on disc, but again, certainly could do that. And again, we have got a cryo option there, so you can take it down to low temperatures. So both very good. I mean, I think it is one of those cases where you do have to do the experiment, and we probably aren't quite understanding what the mechanisms are being driven by, because the typical mechanical properties clearly are not giving us all the answers here.
Right. I have a question. I'm just moving through these questions fairly quickly, Robert, so I apologize for that. As they're now coming in, quite one or two of them, certainly quite a few. Abquat, apologies if I mispronounced Abquat, from Portugal. Did you notice any significant changes in loss modulus or damping behavior using DMA?
Yeah, I'm not sure. Again, Jagita might. We did look at making measurements, and I think the answer was no. But I mean, again, I'm not sure we were able to do those at minus 30. But certainly, I think we did some modulus and damping measurements.
Okay, this is when. Very good. I have an observation from Sam, which is if you wondered how the mechanical results look when plotted as H squared over E as it relates to the ultimate tensile stress. Might more insight.
Yes, I mean, I think you're right, Sam. We could do more with the measurements that we have. So yeah, no, that would be. Yeah, it's difficult because of this ductility. It seems to be giving us more ductile behavior, but it could be that it might relate to the strength of the material. So certainly we could look at that. So that's a very useful suggestion. Thank you, Sam.
And then Santiago, we have a question, I think maybe from Australia. Thank you for a good presentation. Have you tried using the nano impact mode or the NanoVantage to assess single or multiple impact damage?
We certainly have, not for polymer systems. We certainly did for much harder CVD type systems. So I think we looked at boron carbide, for instance, B13C2 type CVD coatings, and we did quite a lot of work looking at how they delaminate under that type of system. So yeah, I mean, you're right. I'm not sure the influence of multiple impacts here, but that could again be something you could look at.
And Robert, one last question I'll take, as we'll then be 10 minutes over, which is about average for these type of meetings.
Yeah.
Can you? This is from Maharaja Japuram. Can you simulate erosion patterns using solid CO2 particles?
Oh, okay. Good question. I'm not sure that anybody's tried that. You possibly could. Yeah, I mean, yeah, we're just sort of moving into this area. So any thoughts of better experimental outcome would be good. But yeah, I've not looked at that. It was a very good question. So thanks very much. You've given me quite a bit of material to get onto.
Obviously, Robert, you can answer any other questions directly from the chat.
Yeah.
And we do have a question and answer session at the end as well, which we'll try and pick up. Sam will try and pick up and answer questions as well. But yes, but you're very welcome to answer directly to the chat, because there were some follow-up comments on the answers you gave as well.
Thank you.
Just looking at that, and Jagit is also doing that as well, which is great. Okay, let me switch into our next speaker, kind of keep things moving a little bit. Mark G is at NPL. He's NPL Fellow in Surface Engineering Tribology. Mark's contributed and authored over 200 papers in his time. Was formerly chair of the Institutes in Physics Tribology Group, and is the new secretary of the Surface Engineering Division of IM3. Materials, mining and minerals. I forget, maybe Mark can remind me what the M's are. And if Mark is there, he can take the stage. We will get going. I'm assuming Mark is there. I can't see him on stage at the moment. There we are. No, Sam, no, that's definitely Sam.
Be showing that, and then he'll be joining live for any questions.
Okay, so I'll let you start it off then.
Okay.
Good morning, I'm Mark G. I'm from the National Physical Laboratory, and this morning I'm going to talk to you about in situ microtribology measurements. So first of all, a brief summary of what I'm going to be talking about. First of all, an introduction to NPL. Then a description of the in situ microtribology test system, examples of its use on different materials. I'm going to talk a little bit about relocation profilometry, which is a useful technique that we've developed, not directly relevant to in situ microtribology, but nevertheless worth looking at, and then summing up finally. So as an introduction to the National Physical Laboratory, it's the UK's National Measurement Institute, which is owned by BEIS. There's a partnering agreement between BEIS and the universities of Strathclyde and Surrey. It's part of the National Measurement System of the UK. Its mission is to undertake excellent science and engineering to deliver extraordinary impact for the UK and provide measurement capability that underpins UK's prosperity and quality of life. Has about 900 staff with 200 visiting researchers per year. We partner with many organisations. We're located on 5 different sites across the UK, and we're focused on the areas of digital, advanced manufacturing, life sciences and health and environment and energy, and we mainly work at TI levels 4 to 7. Moving on to the description of the in situ microtribology test system. So in the picture you see the NPL microtribometer, and this the most important element in this is the series of 8 beams that allow the tip, the indenter can be seen there by the way, to move in a completely linear fashion because of the flexure of these elements. And there are 2 measurement capacitance probes here and here. This one measures deflection of the indenter into the sample, and thereby measures and monitors the load that is applied to the sample by movement through this piezo stack down here. And the other one measures the lateral deflection of the probe, which gives a measure of friction. So you can carry out lots of different experiments with this. Most of these simulate abrasion using single point abrasion, but you can use single positions, multiple positions, static load, ramping load, different diamond radii, different environments. So you can use this ex situ, and ex situ you can use dry and acidic environments, and we've done that. And you can use it, and that's the purpose of this talk, in situ in the SEM to look at detail of what happens to materials. And after experiments, of course, you explore the damage that's occurred by optical microscopy, SEM and FIB SEM. So here you can see an experiment actually being carried out, and here an indenter is lowered against the sample, is then dragged across the surface backwards and forwards, and you can carry this out automatically for any number of repeat scratches. And the beauty of this is you can actually see the detail of the interaction of the indenter with the surface. In this case, you can see debris that is removed from the surface and is produced there. And when you look at high resolution with high resolution images, then you can see the details of the interaction of the probe with the material and how the damage relates to the microstructure of the material. So in the next few videos I'll show you, we have rotated the image and we have captured a series of images automatically that show the progression of damage one to another. So I'll now explore the use of this equipment with examples on 3 different materials: tungsten carbide, cobalt hard metals used as tools all over the place, additive manufactured materials which are of current interest, and DLC coated materials. So in this first example, this is a tungsten carbide cobalt, and you can see the typical structure in the regions away from the scratch of tungsten carbide grains embedded in the cobalt matrix. And the beauty of this sort of analysis is you can see the detail of how the material behaves under the effect of the mechanical overstressing from the in this case diamond indenter. And you can see here that grains of material are fragmenting, they are embedded into the surface of the cobalt, they then flow out from that and into the surface. So for example, look at this grain of tungsten carbide here, which gradually fragments and is reduced to rubble almost. This shows another tungsten carbide cobalt material, in this case a finer grain size material, and you get somewhat different behavior from this. In the early stages of the experiment you can see quite a lot of slip line traces in the grains, but again you're getting fragmentation and fracture in the. And then finally, here's a cubic carbide containing tungsten carbide cobalt material, and if you look at the circuits in circles in particular, here are areas where there were specific grains which eventually accumulate damage and then just break apart and fragment and are removed from the surface. So moving now on to additive manufactured materials. This is an example of a collaboration with Imperial College in London, and they were working on how the processing conditions for additive manufactured stainless steel, and there are 3 different processing directions shown here. They're these 3 images compared to the wrought material shown here, and we're looking at again how the material responds to a single point abrasion process, repeated scratching in a single plane on the material. And here they're looking at details of the differences in deformation that were found between one of the processing directions and another processing directions, and indeed comparing that to the original wrought material. This image shows the edge of one of the scratches, and it shows a lot of the detail to the side. So you can see a lot of slip line traces showing the detail of deformation in grains to the side of the material, and you can see something called conjugate slip, which is multiple slip planes being activated. And one of the features that interested me in particular here was just here you can just about see a crack forming in this grain. So severe damage and failure is beginning to occur here. This is just outlining where that slip area is. This example is a VBN 480 additively manufactured tungsten carbide cobalt material. You can see how the damage occurs at the base of the scratch and the relationship of that with the microstructure of the material. So again, you've got slip lines, you've got cracking, you've got all sorts of damage occurring there. And also, interestingly, you've got these areas where material is pushed out to the side of the scratch itself and eventually delaminates from the surface and is removed. This work was carried out in a collaboration with the University of Manchester and the manufacturers of the material itself, VBN Components. And turning to coated materials, well, in fact, this first sample is an uncoated tool steel. It's rough. It's a ground surface, and you can see the development of the scratch here. And initially, the scratch is deepest where the surface is high and lower where the grooves occur, but eventually it covers the whole surface. You can see how material is being pushed out to the sides of the scratch, and you can see how chips are formed by the material removal process, and you can see one of them in particular there. And it's also interesting to note how the microstructure of the material is changing in the base of the scratch. When you contrast that with a coated sample of the same material in the same condition, you can see that the coating really does reduce damage considerably. Having said that, what is interesting here is cracking that you can observe along the edge of the scratch, and this is like eggshell cracking, where it's deformation under the surface in the substrate that causes high stresses along the edges of the scratch in the coating and then lead to coating failure. This contrasts with the behavior in this experiment, which was carried out on exactly the same conditions, the same sample as the previous experiment. But here, after the first pass or so of the indenter over the surface, you got totally different behavior. So here you can see fragments of coating have just been removed from the surface, and here you see a fragment in motion as the indenter repeatedly moves backwards and forwards over the surface. You can also see in the base of the scratch here, as the scratch develops, that there's a lighter area of contrast, and this is where the coating has been removed completely from the scratch, and it's showing the underlying substrate underneath the coating. So I just wanted to spend a few moments on relocation profilometry. So looking at relocation profilometry now, this is an optical technique which is extremely useful, and this makes use of 3D optical microscopes where you get images as well as height maps. And here, what we've managed to do by careful practical work is locate an area before and after you've carried out a microtribology scratch, and you this is an image before on an uncoated sample, and this is the image afterwards. This is the height map before and the height map afterwards, and you can then combine and register the two height maps and subtract the one from the other, and this dark area here is the actual volume of the scratch itself without any contribution from the original rough surface, and that's extremely useful. So moving on to the another example, this is now a coated surface, and again you've got the two images and the two height maps. You can see the much shallower scratch here, and it's interesting to note that this scratch is only about 40 nanometers deep here, and again you've got the registered and subtracted height maps giving you the information on just the scratch alone. You can then analyze that data, and typically in a scratch you have an area of the groove and an area of pile up, and then the loss area, the material that's actually removed, is the groove minus the pile up area. So if you look at the pile up area, then that's slightly higher for the rough uncoated example, and rather similar for all the other three examples. More interestingly, the groove area decreases, sorry, it's a negative figure, as the sample becomes coated. And here, by the way, we've got two roughness values, the rough example that you've seen already and also an average material, and I haven't shown any micrographs of this one. In particular, if you look at the loss area, which is equivalent to the volume of material lost, you can see that there isn't any difference between the results for the rough and the average samples, but there is a huge result for the whether the sample is coated or not, and this is over an order of magnitude difference here. What I didn't say was we carried out experiments parallel to the lay of the grinding, in other words, parallel to the grinding marks, and also perpendicular to the grinding marks. And frankly, although you might say there's a little bit of a difference here, with more damage in the with less damage, sorry, in the perpendicular direction, then there's not much of a difference, so I wouldn't think that's terribly significant. So summing up, we are showing you an in situ microtribology test system that's been developed for use in situ in the SEM, but can also be used ex situ. We've carried out already a wide range of experiments, and it's used to relate the deformation, the failure mechanisms that you get to the microstructure of the materials that you used, that you have in the materials. We've demonstrated it being applied to tungsten carbide, cobalt hard metals, additively manufactured materials, and coated samples. And relocation profilometry is also a useful technique to examine the absolute value of wear, even to rough surfaces. Thank you very much for listening.
Thank you, Cook. Let me just go back. One of the advantages of having to record the talk so that because of the videos that we had to show is that you've answered some of the questions already that have come in. Stefan asked, what is the force resolution in the normal and lateral mode of your system? And you answered the resolution can be tailored by changing the fixture elements within the current configuration. It's about 1 millinewton. Then Ben, subsequent to Ben, has asked, has made a comment They were very impressive talks, Mark. The AM tungsten cobalt looks to be very different from microstructure. Could you say anything about whether it is good or bad in terms of abrasion, resistance mechanisms versus normal tungsten carbon cobalt with similar percentage of cobalt?
The key point there is it is a different material. So the binder phase there is very much higher than in normal tungsten carbide. I can't remember exactly, but I think it's about 30%. So you wouldn't expect the abrasion resistance to be as high as more conventional monolithic tungsten carbide cobalts. But having said that, the material, I understand, is pretty impressive for the markets that it's designed for. So it's a good material.
Very good, thank you. Robert asked a question. The relocation profilometry is fascinating. Can I ask how you perform the relocating?
Yeah, sure. So my colleague that actually did this work has got very expert at managing to do this. It's by simple stereo microscopy and being able to recognize where you are on the sample. We do use Vickers hardness indenters to give fiducial marks on the surface and then offsetting from that. So we reckon, he reckons, actually I put the benefit where it's due, that he can get to within 3 microns, and that's then enough to actually register the images through software. So there you are.
A question from Santiago. Very, very impressive results. Are all your experiments in reciprocating sliding, or have you done any experiments with abrasion in the same direction, and then in brackets ratcheting?
Right. The experiments, all the experiments we've done have been where the indenter does one stroke and then back again and then lifts off. We haven't done what Santiago is calling ratcheting. It's just the experiments we have done. That's it, really.
Okay. And the last question that I've got here, the last question we'll take is, how do you deal with the debris inside the SEM chamber?
The simple answer is we don't. It just goes into the vacuum system, and eventually it will cause failure of the SEM, I'm sure. But quite honestly, the volume of debris that is created is very small by comparison to the debris you get from other reasons, away in the test system, and deposits from other things going on, and contamination. So we haven't found it to be an issue. Having said that, we by no means use this system all the time. It's infrequent use. So if somebody was running this all the time, then maybe you would have a problem, but we haven't so far.
Very good. Okay, thank you, Mark. Thank you for that talk. Appreciate it. Move on to our next speaker, who is Dr. Stefan Brinkmann from FZ Jülich, Forschungszentrum Centrum. Maybe you can correct me on that, Jülich. His talk is on enhanced nanoindentation by automatic image recognition. Stefan did his PhD at the University of Göttingen. Previously worked at Caltech and Purdue University in the US, and focusing currently on micromechanics and data science regarding micromechanics. And his work is very much to do with nanoindentation and tribology to understand deformation mechanisms. So, Stefan, maybe you can correct the pronunciation of your institute for me, and continue from there. Thank you.
Thank you very much for the kind introduction, and it just translates to research center. So it's a research center in Jülich. So it's Forschungszentrum in German if you care to learn German, but yeah, don't. German is a way too hard language. Anyhow, let's talk about nanonotation in a more abstract way, but also about images like the previous speaker. So if we look at nanonotation as a concept, we have an experiment where we press an object, a hard tip, into the surface, and then we lift it up, the indenter, and then we measure the hardness or the Young's modulus by this method. And traditionally we do that optically, where we, after the indent, look from the top optically, and that's why the Vickers indenter has been so important, because it's easy to identify the corners with the Vickers indenter. But that was very prone to mistakes and difficult, so traditionally, or no, currently, everything is measured by depth. So you measure the depth of the indent during the indentation, and from that you back calculate the contact area. And if we now look at these measurements, the force measurements are rather accurate. I mean, there's some scatter on it, but that's just normal scatter. The depth and the shape of the indenter are a little bit more correlated. So if you measure the depth and know the shape precisely, then you know the contact area. But the shape of the nanoindenter tip changes during your experiments over the months, and also the depth has some inaccuracy because you have the temperature change during your experiment, which leads to drift. You have to identify the surface contact very precisely. Basically what happens if you have a little bit of dust on the surface, and you have instrument compliance, so sample, glue, how good do you screw your tip into the holder. And just as a reminder for those that have not done these theory questions before, typically you measure the force and the depth. From the force and the depth you can calculate the unloading stiffness. From the unloading stiffness you determine the contact area. These are both evaluated, and from that, the contact area, then you know the Young's modulus and the hardness. And if you want to do that, then generally you have to before determine the frame stiffness. Basically, how is your sample mounted? How is your sample glued? How is the tip mounted? You have to know the shape of your tip. That is called the area function calibration, and how this area evolves over time. To do that, you generally use a calibration material. Fused silica is the material of choice, which has a rather low Young's modulus. So if you want to do indentations in, I don't know, steel or tungsten, you do some extrapolation, which is also prone to some inaccuracy. And lastly, I talked before about that the surface contact has to be identified pretty accurately. And that is extremely challenging for high temperature indentation, where you have some temperature drift and everything is moving. So that's where this work sets in, where can we use automatic image recognition to enhance the current use of nanoindentation. And so if we look at an indent in the SEM, this is how it looks like on silicon. You clearly see that in this case the silicon has even broken a little bit, but you kind of see the imprint. And if we now look at the image that we get in this case from a Zeiss microscope, you can see that we get lots of metadata which we then can use to precisely determine the length scale, which is definitely needed. So how large is the indent in this case? And this image recognition is very popular. Even if you drive your car to work in the morning, you might use image recognition to tell you the speed sign on your way to work. And so the first thing that we do is, if we have an image, we we zoom in right now just for you as the audience to observe it more clearly. Then we clean it up a little bit to get rid of all the noise. This cleaning is definitely easier surrounding it than in the area of the indent. And then we can basically threshold it by a lower and upper boundary. So we have basically the black star and the white areas surrounding it. And now we can use this information to determine the contact area. So in the first approach, we use just the black area and use the 3 corners of this black area to identify the corners of a triangle and then calculate the area of this triangle. In the next approach, we use the white area, draw what is called mathematically a convex hull around it, and use this area. That area is definitely too large because it includes lots of plasticity. And the third approach uses the convex hull, which we just identified, but then draws an equilateral triangle into this convex hull circle. And that gives us the third approximation of the contact area. And once we have the contact areas in pixels, we then can use the metadata, which I just explained, to calculate the real contact area. And this is how it looks like in detail. So if we use the blue line is a connection of the 3 black distant points. The orange line is the convex hull of all the white areas. Then we draw a circle around this convex hull and then can draw a triangle into this circle, which I have not shown in this image, just to make it easier and more clear. So now we know the contact area. Once we know the contact area, we can use nanonotation analytics to determine everything like Young's modulus and hardness. So this is a curve that we typically use. We load and unload 5 times with increasing force. So load, unload, load, unload, load, unload, and so on. And we use these 5 unloading cycles to determine the frame stiffness for each sample that we use. So let's say we have 5 unloading circles and 16 indents or 16 measurements, and we have roughly 80 unloading circles, which we then can use to determine the frame compliance for this specific sample. And if we do that, in this case for silicon and fused silica, we see that here are our lines, and they should intersect the y-axis very close, but not at the origin. And if we zoom into that origin, we see, yes, the lines even intersect, but they definitely don't reach the y-axis at the same point. And that's what I really want to drive home here, is that the frame stiffness evaluation, which is the intersection of the blue line with the y-axis, is not constant. So different materials will lead to different intersections points just because you have mounted them slightly different. Once you have the frame stiffness or frame compliance, however you want to call it, you can calculate the hardness and the Young's modulus. The hardness, well, that's according to textbook, force divided by area. The Young's modulus is a reduced Young's modulus, but if you use the Snellen equation, which goes into the traditional way of calculating the Young's modulus during nanonotation, you subtract the compliances, and then you can also, from all the data that you have, you can calculate hardness and reduced Young's modulus. And just as a reminder, the contact area we obtain directly from our SEM results. And the important point here is that I did not have to know anything about the tip shape. Well, I knew that it's triangular, but nothing else. I did not have to identify the surface contact, and all the drift that accumulated during loading did not enter in my evaluation. So those points are rather good. But the real test is how does this method compare to the traditional way of using what is called the Oliver Farr method. And if we do that for the hardness, we see, I told you before, we have these three measures of, or three ways of measuring the area. One is triangle of corners, one is the triangle in the circle, and one is the contact in the pileup. And then we compare it to the traditional Oliver Farm method, right? So the traditional Oliver Farm method doesn't depend on the force. It has a rather low uncertainty, and so it's definitely right now the standard. If we use the orange, if we look at the orange line, for example, we have the contact and the pileup. In these cases, our contact area is overestimated, and so our line makes sense that it's under the reference measurement. If we look just at the corners of our indents and use that to measure our contact area, that's also not very accurately very accurate, because we have cracks in the silicon. Also, these points are not so precisely identified, so that is also not the method of choice. And it turns out, and that was also surprising for me, is that the triangle in the circle is the best approximation. It is not. It has a larger scatter than the measurements by the conventional Oliver Farm method, but it's already in the right ballpark. And for the first measurement of the system without any calibration, we were pretty happy with it. Now, next to the hardness, you can also look at the Young's modulus. The Young's modulus at small forces, we are pretty precise compared again to the Oliver Farm method. However, at larger forces, we definitely overestimate the Young's modulus of silicon, as in this case. But also, I should mention that silicon is definitely one of the more difficult materials to use because it's rather hard, it's rather stiff, so the contact area is rather small, and these evaluations are quite troublesome. So, to discuss the challenges, this data science approach and image recognition has some potential, definitely. Especially we see the great potential at high temperature, where the artifacts that are traditional in measurements are not or don't manifest themselves. This material silicon was definitely very difficult for this pilot study, and we definitely have to improve the algorithms to better identify the contact area. I mean, the great advantage of companies like Google is they have lots of manpower, and they only have to identify whether the speed sign says 60 or 65 miles per hour. They don't have to say the size of this image, and the precise size evaluation is a little bit more difficult. And in these cases, it was very helpful to us to look at the metadata, especially when we want to link the SEM images to the nanonotation positions. The metadata which is saved in all cases in the SEM data and in the nanonotation data is very helpful for this linking, and then we can automatically link the measurements. Yeah. And with that, I want to thank you for your attention.
Thank you, Stefan. Thank you for this very interesting talk. Right, we've got a short time for questions. So one that's coming from Sam is the thresholding performed manually, or is there an algorithm to do it?
Yeah, so everything we do is done automatically. So there's nothing done where I, as a scientist, sit there and change it. In this study, we have used, and you could see it in one of the images, we have also used AFM to correlate it. With grayscales, it's actually pretty easy, because if you automatically rescale the contrast to totally black to totally white, then you can use automatic thresholding to identify the black and white areas, and then you just do some morphological operations to basically clean the image a little bit, because the indent should be larger than, I don't know, 5 pixels and smaller than 80% of the image. So there are some automatic cleaning algorithms that you can then afterwards show on it, but everything is done automatically, yes.
Okay. Thank you. And from Ben, interesting approach. Possibly the lower E at lower force for silicon is related to phase transformation effects? Question mark. Your curves show elbows in unloading that are force dependent. Does the phase transformation with cycling influence the frame stiffness calculation at all?
My gut reaction, of course, is to say no. It does not influence. But that's of course cheating. I mean, as you said, you can see the elbows very nicely here. Those are related to the phase transformation during unloading. So the fit, and I mean, Micromaterials also has a fitting algorithm, right? Runs always from 99%, I think, to 50%. And so in these areas, it's definitely okay. And here one has to slightly take this elbow into account. But very good point, Ben. Very good point.
Thanks. Well, thank you, Stefan. Thank you for the talk. As time's getting on, we'll move on to the next speaker. I appreciate it very much. Our next speaker is Dr. Jan Tomaštic from the Institute of Physics of the Czech Academy of Sciences, and I think Palacký University, if I pronounced that correctly. His talk will be on the characterization of silicon carbon nitride thin films after high temperature annealing. Jan did his PhD at the University of Palacký and was following that was a visiting researcher at the Virginia Tech in the US, and is now a researcher at the Joint Optics Laboratory of the Institute of Physics at the Czech Academy of Sciences and Palacký University, which is in Olujek. Again, you could correct that. His current work focuses on acoustic emission in scratch testing of thin films and coatings. And with that, I'll pass over to Jan for all the corrections.
Okay, thank you, Chris, for introduction. Do we hear each other? Yes, everything okay. So, good morning, ladies and gentlemen. My name is Jan Tomaštic, and I will speak about effect of nitrogen doping on properties of silicon carbide and silicon carbonitride coatings. My aim will be show you general properties, chemical properties, physical properties, and all this stuff. But I will mainly focus on local mechanical properties, which I will be describing. So, let's go to the next slide. To speak about motivation for using coatings is futile on this forum, but everybody knows that coatings are used for several purposes, for optical, for chemical, for catalysis, but we will mainly focus on mechanical properties. There are several grades of coating that are used in general: titanium, aluminum nitrides. These are good coatings, generally used for tools, for motors. They have good mechanical properties, good tribological properties, but the things they lack is resistance in higher temperatures because there is increased oxidation and several other processes. So there's open call for search for new materials. One of these materials can be silicon carbide. It shows an interesting combination of several properties, physical, chemical, and it can be easily modified by doping, which can change other properties, optical, electrical properties. It's easy to prepare using PVD, CVD techniques at low temperatures, and it's used very often. My personally my most favorite use are cosmic electronics, where silicon carbide is perspective to be used in between silicon and because it can endure higher temperature and lower temperature and even higher radiation. It can be substitution for zirconium alloys for nuclear fuel rods. But silicon carbide actually has same issue as titanium nitrides on titanium aluminum nitride. It has problem in higher temperatures. this is the pictures from our own research. You can see scratches of silicon carbide, and on the same silicon carbide after annealing in 900 degrees Celsius. So after exposure to high temperature, you can apparently see some increased cracking, increased brittleness. How to change it? We can, as I said previously, we can dope it. In our research, we have doped it using nitrogens to increase all properties, mainly the mechanical properties and heat resistance. And we have doped it in different ratios so we can watch the results. And we have performed several analyses, composition, structure, but mainly I will talk about mechanical properties and tribological properties. So here are our coatings that were prepared using DC magnetron sputtering from silicon carbide target, and we have used argon atmosphere in our chamber and used and increased the ratio of nitrogens to argon in several different ratios, and these ratios give names to our coatings. So here you can see our several coatings from pure silicon carbide to silicon carbonitride of increased composition of nitrogens, and I will show you very soon how this ratio affected the real composition of elements in this coating. So after annealing, we have performed several annealings, 700, 900, and 1000 degrees, 1100 degrees Celsius. And you can see here how it affected visually our samples. Apparently, there is some interesting coating creation or oxidation layer. To analyze this oxidation layer and to get rid of its effect, we have also annealed in vacuum. We have performed several measurements, but I will mainly focus on mechanical properties and tribological properties. Composition. Different ratio give rise to different compositions. So as you can see, we have something like 1:1 silicon carbide, silicon and carbon composition, and this increased nitrogens to argon ratio increase the nitrogen content. And after the annealing, what happened is that oxygen increased. So apparently we have oxidation here, and nitrogens decreased, and also carbon decreased a little. So we have strong oxygen penetration to the material and creation of oxidation layer, something like 100 to 200 nanometers of thickness. Structure, generally it's an amorphous structure, and introduction of nitrogen leads to formation of SiN-CN and SiCN bonds. And after annealing in pure silicon carbide, there is a creation of silicon carbide nanocrystallites. So it's not full crystallization, it's a partial crystallization of silicon carbon nanocrystallites. And in silicon carbonitride, there is a splitting of carbon-carbon band, there is a graphitization. So we can see the oxygen and nitrogens promotes organization in carbon phase. And what does it mean for mechanical properties? We have measured the hardness. This is the original samples, silicon carbide, the hardest sample, and we have used a different indentation in a different load. So actually we are making depth analysis. Red is the lowest, shallowest indentation. The brown is deepest indentation. So in original samples, everything is similar because there is no surface coating. And after annealing, we can see increase of hardness in all samples in general, but surface effects. Shallow indents show a lower hardness than deeper indents, which kind of means there is something happening on the surface, unsurprisingly, the oxidation layer. Which is this effect is more pronounced in 1100 annealing in air. This is annealing in air, so we can see this effect of oxidation layer be much stronger. But apparently, this whole system have higher values, at least in 900 degrees Celsius, which means there is a increase of hardness, increase of mechanical properties due to short range ordering, but also surface effects due to oxidation. This oxidation effect we have tested using vacuum indentation, because during the vacuum indentation 900 there's no oxidation layer occurred, so we also see there's no depth effect during this indentation, and we just see the increase of mechanical properties. But let's check the tribological tests. We have used progressive scratch tests, the standard scratch test from 0 to maximum load, and analyze it using different techniques. In standard, when we and a lot of you analyze the tribological properties during scratch tests, during pin on disk, and during several tribological tests, you use optical evaluation. We use it also using confocal microscope, which gives a little better resolution than normal white light microscope. Here's some pictures. We more certainly use the depth change record from the nanotest itself to evaluate the cracks or determination of the coatings, the jumps in the depths. And I will speak a little more about acoustic emission, because we have developed our own system of acoustic emission detection during the scratch tests. The system was developed in cooperation with Dakel company from Prague, and this system we have patented. Great thing is it's easily adaptable to any tribological system or nano indentation system. We have it here adapted to nanotests. At the end, we have the record, which we can correlate to previous data, to depth change record, to confocal microscope images. This is how it looks like. This is the normal holder that we generally use in the nanotest platform 3 or in Vantage, and this is how our system for acoustic emission looks like. Actually, it's a piezoelectric sensor embedded into specific holder, and we are using it in connection to our own analyzing unit. Okay, so let's show our evaluation in some specific cases. This is silicon carbide coatings before annealing, and let's say if we will use just one or two analyzing procedures, we can be mistaken. If we can just look a residual image, we can see, okay, something cracked here in the point 1. So coating cracked, and here coating and substrate cracked. So it's like a loss of cohesion of both parts. Generally, we can check it during the depth change record. So we have 3 pass tests. First, topography, just checking the material, then scratch, on-load scratch, and then final topography. So in initial topography, we can see, this is the green color, we can see the coating is okay, but there is some asperity going actually in the above the surface. So like the positive values are into the depth, the negative values are up the sample. And during the onload, the blue phase, nothing happening here. It's like there's just small notch, and coating cracks in fact at the point 2, and the crack is apparently backwards. So the coating cracked backwards and is delaminated, which we can see from final topography. The acoustic emission, let's say, gives another insight and reveals what happened. So the acoustic emission during onload shows that there is some signal. Apparently, let's say the breakage of asperity, probably. There was probably some asperity that was deposited during deposition process and embedded into coating itself. And nothing here. And there is some information, some small signal, some small cracking, which was apparently the cracking of substrate below the coating itself. So it can show us what we cannot see from, let's say, microscopic images after scratch, because if the coating would not crack backwards, we would never see it from the we would probably not see it from the microscopic image. But we can hear it using acoustic emission, and the stronger signal here, the breakage of both coating and substrate. So let's say only microscopic observation can give some insufficient results. We need more insight into the system, into what's happening there using depth change record and maybe acoustic emission, which we are using very effectively. Maybe even stronger use of this acoustic emission detection system for such a case can be shown here. This is a silicon carbon nitride. As I said, silicon carbon nitride seemed to be lower hardness than before than silicon carbide. Okay, I didn't describe during mechanical properties. What was apparent from the graphs that increased nitrogen content means lower hardness, but it cannot be problematic during tribological behavior because lower hardness can mean higher ductility. So, okay, silicon carbon nitride. Here we can see scratch tests, and from the image observation, we would see just something happening here, and nearly nothing happening here. Depth change show us a depth change record. Okay, something happening here during onload. We cannot see it so much. And final topography shows this small jump, but this is in order of like 200 nanometers, which means it's definitely not coating. Okay, I didn't describe the thickness of coating in general. We are talking about 2 to 3 micrometers. So this is like 200 nanometers. So definitely it's not coating itself. It's oxidation layer, which was scratched off. The scratching of oxidation layer we just evaluated and confirmed using EDS measurement. So we have measured this area and we saw the decrease in oxygen signal, which means that we scratched off the oxidation layer. But in the latest part, nothing happening. We couldn't see any cracking. But practically only a sure method to see exact point of what happened, if something happened below the coating, was the acoustic emission, which show us, okay, nothing happening here until this point. And we can see something in depth change, like slow increase of depth, but we have hard time to find the exact point. And I will show you what actually happened, because we have some results from focus and beam. So we used focus and beam. We take out the material and check the cross section. Here in the cross section, we can see the coating and the substrate, nicely adhesive system, no problem there. And in silicon carbide, in pure silicon carbide, we saw cracking occurred firstly on the surface. Sorry, it cannot be seen nicely, but there are like semicircular cracks going from the surface into the depths, and some secondary cracking going from substrate or from interface. It's very brittle system. Silicon carbide can be very brittle in high temperature, and silicon carbon nitride here. This is the highest concentration of nitrogens in silicon carbon nitride we had, and as we saw, we couldn't see anything from the surface. We saw something from the depth change, but not for sure. But we heard it using acoustic emission, and we analyzed the points where the acoustic emission arised, and we just saw nicely. Here, silicon carbon nitride. This is silicon carbide, so we can saw nicely interfacial cracks and cracks from substrate. So actually, the coating prevailed. Coating was very strong, not so brittle as pure silicon carbide, and we have nice result. Just quickly to summarize our results, here are the pictures. We can see in original coatings, scratches in original coatings, some scratch test results. So here LC2, which means critical O2, which means delamination of coating, and some first cracking, LC1. So we have some increase in value of LC1 with the nitrogen content, and we have some LC2, some delamination, but not the same thing in higher concentration of nitrogen. So yeah, coatings failed in some maximum load, but not for higher nitrogen content. And after annealing, most interesting thing, silicon carbide, let's say, deteriorated. There's some brittleness, some cracking, some extensive cracking, but silicon carbonitride actually increase its properties. So we can see some crackings in a low nitrogen content, but not in a higher nitrogen content. We don't see, like for instance, this in middle sample 16 SECN, we can see in S deposition, S deposited case, some cracking, and we cannot see it after annealing. So apparently there are some effects of this changing in structure in structure to mechanical properties. Just some same data shown here in graphs of critical loads. We don't have LC2, we don't have delamination for higher nitrogen content in as deposited sample. And after annealing, we see that LC2 is not happening even in lower concentration of nitrogens. And we also have increase of LC1, the first point of cracking. So here are the some results from a vacuum annealing, which shows that even after vacuum annealing, there is some increase in parameters of LC1, which means the short range ordering increase the mechanical properties. So let me summarize the results. We have deposited silicon carbides and silicon carbonitride coatings. We changed the composition of nitrogen, and we can see that nitrogen content decreased the hardness and elastic modulus, but improved the wear resistant and fracture toughness. After annealing, we can see there is a decrease of scratch resistance and marked embrittlement in silicon carbide, probably due to silicon carbide crystallization, because it's always better to keep the amorphous structure. In silicon carbonitride, annealing doesn't decrease the tribological properties. It's actually prevent silicon carbide crystallization. There is a creation of C2N triple bonds, and it has greater tribological resistance. Okay, thank you for your listening, and maybe we have time for 1 or 2 questions.
Thank you very much. Thank you very much, Jan, for that talk. Just looking to see if we have any questions on the chat. Nothing at the moment.
Okay.
Okay. In that case, I'm going to take the opportunity to catch up some time because we are behind at the moment. If you have any questions for Jan, please just type them into the chat, and he can answer directly to you. And I'm going to move on to our next talker, next speaker, which is Ben. Professor Ben Big. He works at Micromaterials. He's got 2 talks he's going to give now. The first one is how to use advanced nano micro scale testing, and looking at the resistance of DLC coatings. Ben has worked for Micromaterials now for 20 years. As you can tell, I've still got some hair. Not that much stress. But previously, Ben postdoc at Hull, Nottingham and UMIST universities, where he worked on with a range of instrumentation, as I remember. And he's a fellow of the IM3 Institute of Materials, Minerals and whatever the other M is, mining, I forget. And he's a past chairman of the IOP Tribology Group, currently a visiting professor at Manchester Metropolitan Universities and at the Universities of Leeds and Huddersfield. Over 150 published papers, collaborating with many of our customers base around the world, which is probably a decent summary for me to hand over to Ben at this point. Thank you, Ben.
Thank you, Chris. Thanks for the kind introduction. So in this talk, I'm going to be showing how we can use multi-techniques together to improve our understanding of the wear resistance of different diamond-like carbon coatings in different contact situations. So DLC, or diamond-like carbon covers a wide range of amorphous carbon films where mechanical properties can be controlled by things like the sp3 to sp2 ratio and the hydrogen content. And when you add in doping as well, you can imagine you've got a very wide parameter space that coating designers can develop materials within. And what is very attractive to these systems is that they can be deposited with high hardness and low friction, but typically with relatively high compressive stresses, which can be partially beneficial, but equally can be responsible with poor adhesion and durability in highly loaded contact. So we were interested in studying this, and this has been known for some time. This on the right is a schematic by Derek Arnell, right back sort of 40 years ago now, looking at showing essentially low wear rate for DLCs in low pressure contacts, and then an abrupt transition to a high wear rate regime. So what I've sort of dashed there and just adapted his figure essentially was a couple of different, a red and a blue line there, is that we might be able to develop multi-layer coating compositions or doped coating compositions that don't have a severe failure mechanism compared to the normal undoped DLCs, and that could be attractive if in applications where these things are subjected to occasional high pressure contacts. So in this talk, I'm going to be using a wide range of the different test capability in the NowTest Vantage system. So we're going to be using both loading heads. We're going to use all the different modules. And really what we're trying to understand is the correlation between the mechanical properties we measure in these coating systems and their tribological behavior in these different types of tests, and really try to get behind what is the relationship and what causes that relationship. So we're going to be using indentation to get the properties. We're going to do scratch testing at nano and micro scales, reciprocating wear with our new nano tribo test, and also a little bit of impact testing as well. So as Chris introduced it right at the beginning of today, that we sell 3 instruments, and the one that is a sort of flagship instrument for general use is the NowTest Vantage system. And this is a modular multifunctional system that combines multiple different test techniques: indentation, scratch, impact, fretting, and now this nano tribo test, and that's the 5th one, with 2 different loading heads, allowing it to perform tests on the nano and the micro scales, different test environments, which I won't talk on in today's talk, and also different test environments, which you've just heard from Jan, can be particularly useful multi-sensing acoustic emission to give you additional information about failure mechanisms. So going to be looking at 3 different coating systems. So one has a DLC, an undoped DLC top layer, another a silicon doped DLC top layer, and another a tungsten doped DLC top layer. And these have all been deposited on hardened M2 tool steel substrates, and a couple of them with the Hauser system at Leeds, and also one was a commercial system. So if we look at their mechanical properties, we can see on the left there that the undoped DLC is more resistant to indentation contact, and when you analyze the curves, then you get, typically that has a hardness of about 25 gigapascals, and the softest at the other end is the tungsten doped one, which is about 13 GPa. So you can see on the right the mechanical properties as a function of depth, from indentation depths to different load levels, and you can see they're relatively invariant as a function of depth in this range. So this is all about under 1/10 of the coating thickness. So also you can use isotype approaches to get accurate elastic modulus measurements, and that was important when we simulated their behavior. So scratch testing, you've heard a lot about the importance from Mark and from Jan about the importance of these single asperity tribology tests. They're particularly useful for simplifying the complex conditions that occur in things like abrasion. Also, you've just heard about testing thin coating systems. But maybe another word on the right, if we look at this classic picture from Kathy Weil and Greg Sawyer about how and why we might do these single asperity contact tests, is because in a classic macroscale tribological test, such as in a pin on disc test, the real area of contact is only taking place at the tops of the asperities on the slider and the surface. So that real area of contact is a much smaller fraction of the nominal area of contact. And these contacts are therefore at much higher contact stresses. So if you really want to try and understand what's driving the deformation in your material, then it's a very useful thing to simulate these high stress contacts, and we can do that in our single asperity nano or micro tribological tests, where we have a hard asperity or probe tip sliding under very carefully controlled contact conditions. So you've heard a little bit from Jan just now about the 3-scan procedure. This is something we developed over a large number of years, and this has recently led to a nano scratch standard that Mark G and myself and others have been working on for a long amount of time, and that's finally been published. And in the test that I'm going to describe now, we've looked at nanoscale scratch tests with the low load head with a sharper probe, a 5 micron and spherical contact probe, and in the micro range with a blunter 25 micron probe. So very, very simplified picture now of the depth of the peak stresses for plasticity, for example, in a coating system. So what we can see is as we change the probe radius, we change the depth at which those peak stresses are developed. And if your mechanism involves substrate yield through plasticity, then this is clearly the results you get are going to be very, very dependent on where those peak stresses are. Obviously, it's more complicated in the sliding contact system, and I'll show you where we can model this and get more accurate data. So experimentally, if we do the scratch test on these 3 different hard coating diamond-like carbon systems with this 5 micron spheroconical probe, what we can see is that they're very different in terms of the LY, which is the critical load for the onset of plasticity, and the LC1, which is the critical load for the onset of cracking in these systems. So what we can see is that the hardest coating system here has the highest critical load for yield. Conversely, this system here, the tungsten dope one, has a very low critical load for yield, but it didn't crack before the peak load of the nanotest system was reached in these tests. So there's a clear correlation between the mechanical properties of these coating systems and their behavior in these tests. So we can simulate that with another optional module in the nanotest, which is this integrated SIO software, in this case the Scratch stress analyzer, and we input the data from the indentation testing. Constraint factor is also very important, and this allows us then to simulate the stress distributions that are developing in these scratch tests, and we can get information about the von Mises stresses, information about the normal stresses, and information about the interfacial shear stresses. So this is an example here looking at the von Mises stress distributions at the onset of yield. So in each of these cases, the scratch direction is from left to right, illustrated by this arrow here. And the red areas are the highest stresses, the blue areas are the lowest stresses, as you can see if you can just make out the key there. And these hashed regions are the regions at which the stress developing that contact is higher than the yield stress of that particular part of the system. And straight away we can see some clear differences in these systems. We can see for this guy it's very overloaded within the coating. Conversely, when this harder system yields, it's actually within the steel substrate and it's actually not within the coating. So this has differences in terms of their wear resistance in nanofretting tests and things like that. We can also look at tensile stresses. These form at the back of the sliding probe. You get this maximum here at the back. And you can see that even though the critical loads in nano and microscale scratch tests are quite different, actually they actually correlate to quite similar tensile stresses in these tests, suggesting that there's basically a similar mechanism or the same mechanism going on. So if we look now at critical loads at failure, what we can see is actually this soft disk system, this tungsten dope system, actually has much higher critical loads at LC1 and LC2. And we can look at interfacial shear stresses as well. And when we do that, despite these differences in LC2, when we actually do the calculations within the SIO software, actually we see the stresses at the interface are really relatively similar. So that suggests that actually it's the mechanical properties of the systems that are giving the apparent differences in adhesion as opposed to a true interfacial difference between these coating systems. So we can also measure the friction throughout these tests. And when we do that, we can understand how the friction varies as a function of load by applying these two-term equations where you split the measured friction into an interfacial component and a ploughing component, which is depth dependent in the system. And in this equation here, this parameter at the front here is dependent on whether the load is supported on the front and the back faces of the sliding probe, or whether it's just supported on the front of the probe. So we know that information because we have the depth recovery during the scratch recovery in the test. So therefore, when we come to fit the frictional data as a function of depth, we can actually accurately fit this transition where we're seeing this gradual increase and then this quick, more rapid increase, this sort of bilinear behavior here. And we actually fit that with this equation here, which is quite nicely because we have this depth-dependent information here. We can also use those same parameters to fit the nanoscale scratch test, and this is reasonably encouraging fit with exactly the same parameters. And what I've shown so far essentially is that this picture of understanding wear rate and contact pressure, actually if we consider the depth of the peak stresses, then we have some better understanding. What we can say is if the peak stresses are well within the coatings, then relative abrasion resistance is controlled by this factor of Y over E. But at higher load, plasticity in the substrate becomes important. So we've looked a little bit further at these sliding contacts with our new NanoTribo test. So here we have an additional stage here, which we control within the NanoTest software. And it rapidly goes backwards and forwards here. And this allows us to perform the very high cycle tests, very long track sliding distances, and we can even combine with electrical contact resistance measurements. So just to emphasize, this new module really expands the range of test capability, the nanotribological test capability that we have within our NanoTest Vantage system. So it allows us to achieve really very, very high sliding distances in comparison with what might be more normal in terms of a nano scratch test. And higher speeds. So we're accurately recording the evolution of friction throughout the test. So this is the raw friction versus time data, and you can see over a few cycles here. In this case, this is a transition to a higher friction regime. You can generate friction loops from this sort of thing. And this is typical behavior that might change as a function of load, depending on topographic influence, ploughing, transfer films, and things like this. And this one here is just a typical example of 3 different repeat tests. In one of these repeat tests, you can see that it's much more jagged friction versus cycles. So we've done some SEM in collaboration with Manchester Metropolitan University. And what we can see here is that there's partial failure over that track. Some regions are intact. Some regions you have this fracturing. And then you get this exposure of the tungsten coming from the sublayer. So essentially you're getting a cohesive failure mechanism within that coating system. And that's quite important in terms of coating design. And it's a bit of a limitation. So we've looked a little bit more detail at that with our impact test capability. So those that haven't seen it before, essentially think of it like a little bit like a woodpecker tapping at a material. And so we fire this probe in backwards and forwards, and it generates multiple high stress contacts, true impact events that allow us to fail materials at high strain rates. And when we compare these three different systems, if you remember, this is the hardest one with the best wear resistance within most sliding tests. This has the actually lower wear resistance in the sliding test, but nevertheless, you can see in terms of impact resistance, much more cracking resistance. So you're getting a sort of indentation type crater, not a cracking beta. You see a couple of ones here where it hasn't failed. So if you look in a little bit more detail, you can really see that interfacial failures are the cause of the headache in these coating systems. So you see you're getting exposure of these sublayers, and in this case, exposure even of the steel substrate underneath. So hopefully what I've shown you is that there's no coating is perfect in every test. So if we're designing coatings, we really need to design these coating systems with a thought to the actual applications that they're likely to be exposed to. So in this summary here from one of the papers, we looked at wear resistance, friction, etc., and the relative ranking of these coating systems. Maybe it's more easy if we look in terms of properties such as the hardness modulus ratio, where we just say plus is good and minus is bad, and you can see there essentially how these coating systems are behaving. So hopefully I've given you a flavor of how, when we do this multifunctional characterization, it really gives us a lot of insight into why coatings perform well in some conditions and not others. And it really helps from a coating design point of view. And that once you have that fundamental information about why things happen, then it enables you to start to design better systems to mitigate these things. So one point, I didn't really stress this hard enough, but if you have particularly repetitive impact, that you shouldn't always aim for very high hardness in the system. And this is maybe a cheesy point, but we do call the system the now-test vantage, and you do see more from a vantage point, particularly when we keep adding things to the system. And so there's a list of papers there that you're welcome for more information, but we can send these to you as well. If you feel free to email me if you want more information about that. Okay, that's it for me. Thank you on this one. So what do we want to do next? Do we want to answer questions on this one next?
Yes, I'll take whatever questions we have. Sorry, missing the go on stage button. Keeps moving as my screen reformats.
If there aren't questions, that enables us to
I mean, I think you can just go on to the second of the talks which you're doing for Adrian. Got from Stefan. For the simulations, do you account for the delamination?
No, I think it's the answer. I think these are sort of what the simulations can do is they can allow for topographic differences in so the profile. So if there is wear and the profile is changing, we can allow for that. But it doesn't catch, for example, interfacial delamination and things like that, as far as I know. There might be other modules within the SIO film Doppler packages and things that do, but in the ones that we use, it essentially is catching differences in topographic profile. I don't know if that's answered it, so maybe half answered it.
Okay, very good. So let's move on to kindly doing a talk instead of Adrian on new developments at Micromaterials, including the high temperature, high speed mechanisms.
Yeah, it's the things that we put together in a bit of a rush.
Yeah, micro impact, micro warebox, soft sample work, and cold stage development. It's and I'm sure other things beside, but so if I just I'll hand back to you and let you get on with it.
Okay, thanks very much. So this is something that Adrian and I put together to highlight some of the new developments, not all of the new developments, some of the new developments we're working on over the last 18 months or so. So you've heard a little bit already about multi-sensing. You heard from Jan particularly about the acoustic emission and how nice this was in terms of giving additional information about the onset of failure in scratch tests. We've also worked with Jan and Radim and colleagues about how we integrate this. Adrian and I have been looking at with impact as well. So it's particularly useful looking at subsurface failures. With the Tribo test, I just talked a little bit about that, so I don't propose to again, but we've also integrated that with an electrical contact resistance capability, and that again provides us additional multi-sensing capability. So in this talk, I actually thought I'd focus on the things on the right, and most, but not all of these new things are coming through within the framework of this new Platform 5 operating software. So those that don't know about that, so this is something that we've launched of a brand new operating system for the Navitas Vantage system, and it allows us to do soft sample contact, improve soft sample contact routines. There's a brand new scratch package within it, scratch and wear package. We also have this capability to do mechanical property measurements at high speed at different length scales. These nano wear tests, again or wear boxes if you like. And I just thought I'd say a little bit at the end about our DMCT test, which is our equivalent to the CSM mode. So when we think of performing measurements on extremely low stiffness materials, this is quite a challenge for an indentation system, because when you detect contact, you have to have something that says, right, I've detected contact, now I can apply the load. So if you have a typically stiff in the direction of the loading head system, then it's very, very difficult to detect that additional stiffness from the contact. So this flexural stiffness of the loading head determines the ability of the system to detect contact. And if you look at how the nanotest stacks up against any other nano indenter, you'll find actually we're uniquely suited to very accurately measure these low stiffness materials. So we have a very low stiffness loading head, so consequently that means that we can detect low stiffness materials more easily because they're a bigger fraction of that loading total stiffness that you're measuring. So just some examples. I won't go into. We'll hear more about this later in the year, I think, from Richard. Richard's going to at NCATS, which will talk in more detail. But essentially, just to show that these measurements here down at sort of kPa stiffnesses, single digit kPa, and to show differences between things with cross-linking. This, as far as we know, is the first time this has ever been done on a nano indenter system. So if you think about the nanotest, and maybe traditionally you think, oh, that system's ideal for tribology, or it's ideal for high temperature, stiff engineering materials. Actually, we have some considerable advantages for soft materials as well. This is just a couple of little examples of this new scratch package, which is Steve has completely redesigned this. So we've arranged for analysis, report writing, to different load profiles, statistical approaches, integrating with the microscope. There's a whole bunch of new things in there, and we're quite excited by that, and we're still learning about the capability that we can do in that system. We also have this ability to look at the very fine scale mapping and rapid mapping with the Platform 5 in conjunction with the nanopositioner stage. So if you have this nanopositioner stage, the SPM nanopositioner stage in your test, it really allows you to get the most out of Platform 5. So here's something that Adrian did, looking at a zinc alloy coating. So this is like a 10 by 10 topographic image of the surface. So again, it's just designing, this image is not there to create the prettiest image in the world. This area is used to create a topographic map that can be used to precisely position the indent in specific phases. In this case, what Adrian's then done is he's zoomed in there and said, actually, what I want is a 10 by 10 matrix of indentations within that 1 by 1 square micron area. So obviously, if you make the indents too big, then they're just going to overlap. So in this case, Adrian switched to a very sharp cube corner indenter, very low load measurements. And when he does that, interestingly, he can very nicely reproduce the different mechanical properties of the different phases in this material. And it's quite nice in this case because you can see that the hard phase in this system is actually the least stiff as well. So you can see that these are true mechanical property measurements. They're not being influenced by the topography of the system. The other things you can do with this system is you can stitch multiple grids together. You can, there's an advanced statistical package now for pulling out the individual properties of the different phases in a system. You get nicely, if you want, you can get some very decent quality images. This is some work from MPL, and what we see here, this is a cemented carbide, very similar to the one that Mark showed earlier. And here is a nanopositioner image of exactly the same region. And you can see essentially you're in the nanopositioner image, you're reproducing the SEM quality map. And again, because you have a very stiff system, in this case, this is a grain, a biomaterial with some grains in it, and the probe itself is not being affected by having these topographic differences of the grains. Okay, so this is again something new to us, something I've done a long time ago in my previous job in AFM, which is to use to do essentially a wear box test where you can have a highly loaded region and then then a topographically scanned region, and this allows you then to differentiate that height map between these two regions. So this wear box module now in Platform 5 has been developed with as much flexibility as we can think of, so we can perform any range of different combination of wear cycles and topographic cycles. And typically with the topographic cycles, we're keeping those loads very low, typically the order of 1 micronewton. And then we can export the data for quantitative analysis of wear volumes. So this is some work that Adrian did, in this case looking at a 750 micron thick amorphous carbon thin film. In this case with a spheroconical probe, 5 micron in radius, and he just did some repeat tests in the central region at 50 millinewtons. And if we run through the test, you can see how that wear scar evolves. Oops, excuse me. And as Robert Wood was saying earlier, the shape of this wear scar again determines about whether this is brittle or ductile deformation as well. So there's a wealth of information in there that's very useful when it comes to doing these type of tests. And the last thing I wanted to say was something about continuous stiffness measurements. And it's not my usual approach to criticize competitor data, but this image on the right is still quite an important image figure, because this paper is still referenced by the standard as potentially the best approach to try and mitigate the problems with the continuous stiffness measurement. And in the upcoming standard at the moment, it says if you minimize that oscillation amplitude, you can minimize the problems on soft samples. So what we can see here is these are indentations on a copper 100, and the SEM area measurements with this competitor system. So this is the true hardness. So this is, as Stefan was saying earlier, you can measure the contact area accurately through an SEM and apply one of the corrections that Stefan's talking, and that allows you to get the true measurements. It's a little bit worrying. There's a scatter there, but nevertheless. So what we're seeing is that as these amplitudes increase, the measurements get more and more and more silly, and maybe there's probe bouncing, all sorts of things are going on, and particularly in this low load regime, it's not very nice at all. So the standard's pointing you in the direction of saying, well, you could mitigate some of the problems by going to low loads, but it doesn't really suggest that you've necessarily fixed the problem. So this is one of the things that have been bugging us for some time with our own continuous stiffness analog, which we call DMCT, which Jim, our founder, has been working on for a number of years. And what we've come up with now, essentially, is an improved contact detection advantages through this plectrum of the system. We've improved our experiment design approach, and maybe we may yet patent this, so maybe I can't say what it is. And we've improved our analysis approach. And when we do that, we can see that we get really very nice data on the exact same, nominally exactly the same sample, right down to 30 millinewtons, no problem at all. If we go back to the competitor data and we look, what would 30 newtons be, nanometers be, we would just be well within the range of nonsensical data. So we do have this additional test capability. We don't show it off much, but we do feel that there's a potential great scope to expand our capabilities in this area, because we do think it maybe potentially has a lot more advantages over the competitors. And so that's what I talked about in red. What next? We're always open. We essentially are going to develop things that are interesting, but also commercial. So we're very interested to hear from you. You'll have maybe seen some of the poll questions throughout the day. And we're trying to get a handle on what things are particularly interesting to people. So, and please approach us with ideas and things like that. So, okay, thank you very much.
We've got some questions here. I'll ask the ones that are relevant to the talk, and then I'll open up for Q&A as we advertised. But first question is from Guzi. He asked the question, just as I lose that, how is LC1, LC2 determined?
We're looking at things like the friction changes and depth changes, rather than using maybe optical to confirm. But in this case, we were using LC1 and LC2 from friction and depth changes in the system. So we're assigning LY as yield, LC1 as the onset of cracking, and LC2 as the onset of total failure of the coating system. So actually, you can get many more failures, and you may be able to assign different ones. But just for simplicity, we've just assigned that terminology essentially.
Okay. Then for Stefan, regarding the DMCT, what is the frequency?
Good question. I think this isn't one of these ultra high frequency ones. This, as far as I know, was done at 40 hertz, but I might be. I would need to double check, but I think 40 hertz.
Okay. Roots. Okay. I have then comment from Sam, which is there can be up to LC5, depending on your classification. She's true. Stefan said 40 hertz is great, which is good. Always good to get the right frequencies, or good acceptable frequencies at least. Right. The last part of the meeting was a Q&A session. This is basically designed for, particularly for our users, to ask us any questions that they want. Try and keep them polite if you can, but yes, I think yeah, basically it's the chance to put those. Well, so I'll kick the ball up by asking Ben a question, which on the.
But you're not a Nanotest user.
I know. I'm going to kick the ball off by asking you a question that just entered my head because of the questions that have just come up. Right, talking about frequencies, working at 40 hertz, Stefan says is great, it's good. But what's the advantage or the disadvantage of working at 200 hertz, which is often what we see advertised for DMCT, continuous stiffness, dynamic type measurements? Is there pros and cons? Are there any?
Well, I think if you're slightly higher stiffness frequency, then you can approach more elastic contacts better, and then so the underlying assumptions of the maths that there's not any plasticity occurring in the force removal segments. So that's really where it comes, where there can be some benefit. But if you go to the very high frequency stuff, then it's a little bit more complex on the analysis side of things.
Okay. Stefan says 200.
Well, there you go. So Stefan knows probably a lot more about it than I did then, by the sound of it.
Okay. There you go. He says it's a default fix of European electrical network. Therefore, you get some artifacts. This is interesting.
Okay, thanks.
Comment. Okay. It seems that everyone out there is happy with their Nanotest, at least publicly so. Okay. Well, I think in that case, as we have hit, we're 5 minutes past the point of the meeting when we should be closing. I think there's a couple of little things to put up still, which is a connection to our LinkedIn page for further information. So this our LinkedIn page, where you can get to through that the link there, is basically where we put up all our adverts for future meetings. It's also where we put in announcements of new papers and technical literature. It doesn't get used very much for plain marketing. It's normally papers, application notes, and news on technical talks and seminars which are upcoming. So it's quite a decent one to follow or subscribe to, whatever the terminology might be for LinkedIn, which I do tend to forget. And the other place where you can get technical information, of course, is from the web page, which is markingmaterials.co.uk, which has just come up there. Obviously a lot more static than the LinkedIn page, but contains a lot more information as built up over many years of expertise, and is a useful resource, I believe. There's also the place where, if you're a user of the Nanotest, you can access the user page, which has the resources such as the latest version of the software and manuals. So you will need a password for that as a user, which you can get by sending a note to Micromaterials with your serial number and your place and location. Of course, if you haven't already got the password within your group. And that's that's where you can get the latest information on software and manuals and such like. Okay, leave that up for a minute. Otherwise, I'd like to thank all of the speakers: Robert, Mark, Stefan, Leanne, Ben, and Adrian, for preparation of the work, particularly. And I hope next year we can do this face to face again. Maybe if we're brave, but it's obviously a very short replacement for the all-day meeting that day and a half meeting that we traditionally hold. But I hope it was interesting and useful. And I thank everyone who's attended. At the end of this call, you will get a thank you email, but it will also contain a link to the recording of this call. Please feel free to share that recording with link with your colleagues and your friends, and anyone who might have an interest in the subject. So on that, thank you very much. Thank you for joining. Thank you for speaking, and I wish everyone a good day, and eventually, not too far, a good Christmas and New Year holiday. Thank you.
Nice.
Thanks. Bye-bye.
Bye-bye.